Hi friends, we will see about velocity analysis with respect to instantaneous center method. So we need to determine the number of instantaneous centers, this capital N, using the relation. You know very well, n is equal to n into n minus 1 divided by 2, and small n is the number of links specified. So make a list of all the instantaneous center rotation in the mechanism. Locate by inspection the primary ICRS, that is instantaneous center radiuses, and mark them by solid lines on the circle diagram, that is I12, I23, I34 and I14. Locate the secondary instantaneous center radius using Kennedy's theorem. If three bodies move relative to each other, they have three instantaneous centers and they lie on a straight line. To implement Kennedy's theorem, look for quadrilateral in the circle diagram and form diagonals. Clearly, each diagonal, say 1, 3, will form two adjacent triangles 1, 3, 4 and 1, 2, 3. That is, each diagonal will form two pairs of three bodies in relative motion, to each of which K and dt, Kennedy displacement diagram, so and can be applied. So I13 will lie on the intersection of I12, I23, three bodies 1, 2, 3 and I14, I34. Three bodies 1, 3, 4 produced if necessary. So I24 will lie on the intersection of I12, I14, three bodies 1, 2, 4 and I123 and I34. So three bodies 2, 3, 4 produced if necessary. Step 1. Before that, we have to know omega AB is given, that is, and omega BZ and omega CD are to be determined. Step 1. Perpendiculars to the known direction of velocities B and C. Help locate the instantaneous center at O. The point B belongs to both link AB, the pure rotation about A, the link AB under pure rotation about A, the link BZ under complex motion equivalent to pure rotation about A, that is omega AB into AB is equal to omega BZ into BO. Omega BC already known by now. Omega CD into CD is equal to omega BC into CO. Step 3. The point C belongs to both the link CD and a pure rotation about D, the link BC under complex motion equivalent to pure rotation about O. Locate all the instantaneous center of rotation of slider crank mechanism as shown. The lengths of crank OB and connecting rod AB are 100 and 400 mm respectively. If the crank rotates clockwise with an angular velocity of 10 radian per second, so we need to find the velocity of slider A and the angular velocity of connecting rod AB. So omega OB is equal to 10 radian per second, OB is equal to 100 mm, that is 0.1 meter. So velocity OB is equal to EB into omega OB into OB, that is equal to 10 into 0.1, that is 1 meter per second. So capital N is equal to n into n minus 1 divided by 2 is equal to 6. So from which we have analyzed the velocity. To implement Kennedy theorem, look for quadrilateral in the circle diagram and form diagonals. Clearly, each diagonal, say 1, 2, 3, will form two adjacent triangles 1, 3, 4 and 1, 2, 3. That is, each diagonal will form two pairs of three bodies in relative motion, to each of which Kennedy can be applied. Theorem. So I13 will lie on the intersection of I12, I23, three bodies 1, 2, 3 and I4, I34, three bodies I34 reduced if necessary. I24 will lie on the intersection of I12, I14, three bodies 1, 2, 4, and I23, I34, three bodies 2, 3, 4 reduced if necessary. So I13 is equal to 460 mm is 0.46 meter, and I13B is equal to 560 mm 0.56 meter. Velocity of the slider V is equal to velocity of slider A. We know that VA divided by I13A is equal to VB I13B. So VA is equal to VB I13A I13B. So is equal to 1 into 0.46 divided by 0.56 is equal to 0.82 meter per second. Omega AB is equal to VB divided by I13B is equal to 1 by 0.56 is equal to 1.78 radian per second. Velocity analysis. So rubbing velocity at a pinpoint. So rubbing velocity at the point O is equal to omega 1 minus omega 2 into R if the links move in the same direction. Omega 1 plus omega 2 into R if the links move in the opposite direction. Case 1, 2 points in the same body, that is equal to velocity differences, that is VP is equal to VP minus VA, that is 2 points in different bodies, relative velocity. Another set of sections, VPA and relative velocity is the resultant. VPA is not perpendicular to the line joining P and A when P and A are not on the same body. The resultant vector is different. So velocity analysis, that is velocity of slip. Both the links forming the sliding joint are not grounded, implying a floating sliding joint. Notably, point A belongs to two different bodies, namely 2 and 3, implying case relative velocity. Axis of slip, line along which sliding occurs between links 3 and 4. Axis of rotation, the line along which we can transmit motion or force across the slider joint, except friction assumed negligible. This is the velocity of slip. Intuition, the axes of 3 and 4 have fixed geometric relationship. Hence, the rate of change theta 3, theta 4 will remain the same. Omega 3 is equal to omega 4. VA3 is equal to VA2. And draw the axis of flip and the axis of transmission through point A. Start the end of a linkage for which you have the most information. Calculate the magnitude of the velocity point A as part of link 2, that is A2. So VA2 is equal to AO2 into omega 2. Project VA2 onto the axis of slip and the axis of transmission to create the components VA2 slip and V transmission of VA2 respectively. Note that the link 3 is pin jointed to link 2. So VA3 is equal to VA2. Then note that the direction of velocity of point VA4 is predictable since all the points on link 4 are reverting in pure rotation at point OA. Draw the line PP through a point A and perpendicular to the effective link 4 O4. Line PP is the direction of velocity VA4. Construct the true magnitude of velocity vector VA4 by extending the projection of transmission component Vtrans until it intersects LPP. Project VA4 into the axis of slip to create the slip component VA4 slip. So V slip 42 is equal to VA4 slip minus VA2 slip. Write the relative velocity vector equation for slip components of point A2 versus point A4. The angular velocities of links 3 and 4 are identical because they are shared. The slider joint must rotate together. Omega 4 omega 3 is equal to VA4 by VA now.